Hey, what's going on, YouTube? What's up? I think that we're live. Let's see. YouTube Studio. Where'd it go? Oh no, I lost the tab that I was looking for. What's going on? We should be live on the right channel. I think we are. Studio.youtube.com. I totally lost the tab. I think that we're live. Go live. Yeah, I think we are. Okay, let's get chat up. What's going on, everybody? How's it going? My name's John. This is a brand new channel. I'm calling myself the Math Hobbyist. So this is gonna be fun. We have worked all of these problems. Look at all these lovely problems. We've done 1 through 8, 10, and 11, all from Strang's book. We've worked a few from Shilov, and I did also just download Axler as well. So I know that Axler's linear algebra book is highly recommended by everybody. This is another one of those that people say is like a work of art. His book is Linear Algebra done right. So that's funny because what he means by done right is that he doesn't introduce the idea of the determinant until way later in the book. Whereas Shilov, the other advanced linear algebra book that we added, includes determinants immediately. Like chapter 1 is determinants, and we've only done determinant problems. So that's interesting. What's up with that? What do you mean? Mathematicians can disagree with one another? What? Does that happen? Yes, it does. So, this is a little baby linear algebra, and these two are both big boy linear algebra books. First course and second course. So we are mixing in problems from different difficulty levels, and I'm excited. Let's keep going. Let's get started. So Strang, let's just jump into one of them. Strang number 9. What does Strang 9 look like? I like that green pen. Where did it go? I think the green is a nice color, right? Strang 119. What is the problem statement? Also, let's see. I hope I don't have subs only on or anything like that. How's it going, everybody? Hello. Is it your first time here? Thank you for tuning in. Hit the like button, everybody. That would help. Alright. It says, in the XY plane, mark all 9 of these linear combinations. Okay, so we have two vectors, 2, 1, and 0, 1. All right, so it said mark all 9 of these linear combinations. Why are there 9? It's because we have 3 options here, and then we have 3 options for the second one, and, well, 3 times 3 is 9. So let's figure out what that's going to look like. Let's switch to yellow. Why not? Solution. I'm going to just create a table. Let's just create a damn table. Why don't we do C comma D, and let's just list them all. 0, 0, 0, 1, 0, 2. Boom, boom, boom. 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 And then we could give this thing a letter V and this thing a letter W. You know what? I think at this point people can pause, rewind. Let's just do it in one step. What does CV plus DW equal? So if C is 0 and D is 0, we're multiplying both of those vectors by the number 0, so this is going to be 0, 0. If C is 0 and D is 1, then this is going to be the vector 0, 1. If C is 0 and D is 2, then we're going to double D, and then we're getting 0, 2. Now, if C is 1, 2, 1, if we add the two together, this is the first one where they're combining. We've got 2, 2. So 1 of C plus 2 of D is going to be 2, 3. 2C, 0D is 4, 2. 2C1D is going to be 4. 2 plus 3, or 2 plus 1 is 3. Yeah. 2 and 1. 2, 2. So we've got 4 for the first coordinate, and we have 2 and 2. So we've got 4 as well. So those are our 9 vectors. Hey, Paulo, how's it going? Hey, I bought the book a couple months ago. However, I just feel like it gets quite advanced with the proofs. I see. Are you talking about Strang or Shilov or Axler? Because all three of them have a different amount of mathematical difficulty. So all of them are proof-based. All of them definitely have proofs, and that is a challenge about linear algebra. I think it's often the first time that people see proof-based mathematics at all. And it can be scary, and it can take a little time to wrap your head around it, but proofs are beautiful, dude. Proofs are beautiful. I love proofs. So let me just draw a little heart for that. Heart. Proofs. Proofs loves linear algebra, and linear algebra loves proofs. It's a cool class, honestly, because linear algebra is both theoretical and proof-based, and you can study it very abstractly with just pure proofs like this guy or this guy, or you can do a combination of the two like Strang does. Strang definitely mixes in more calculation with proofs, from what I've seen so far. Anyway, so that's cool. Yeah, which book is it that you struggled with? Because they are proofs just take time, no matter what. No matter what. Okay, so these are all, I notice, all positive coordinates. So let's give ourselves some space. And I'm not going to draw arrows everywhere, I don't think, because that would be madness. 0, 1, 0, 2. Why don't we at least use a different color, though? I don't know. Red looks like it'll pop. We've got 0, 0, 0, 1, 0, 2. Oops, I wasn't even drawing that right. 0, 0, 0, 1, 0, 2. That's what I meant. Let's just restart. Okay, we can do this. We can do this. 0, 0, 0, 1, 0, 2, going upward with these. Now we've got 2, comma 1, 1, 2, comma 1, 2, comma 2, 2, comma 3. Now we've got 4, so let's give ourselves little tick marks. We've got 4, comma 2, we've got 4, comma 3, and we have 4, comma 4. So if we wanted to draw all of those vectors, does it, in the xy plane, mark all 9 of these linear combinations? I don't know if it wants us to draw all the vectors. Is it valuable? Is it valuable to draw these? It's kind of messy, but we can do it. This is craziness. Look at this. This looks like a badass, like it's like a bunch of arrows, like a battalion, like shooting arrows out somewhere. Like, that's cool. All right, so I don't know. I think that's what. Oh, you got Sheloff. Sheloff is tough. That's what I'm seeing so far. Yeah, I've just gotten into it a little bit. Sheloff has been tough so far. I feel you. You took it in college, might give it a shot again. Give it a shot with us here on stream. Let's all work linear algebra together, man. It's cool. The book we used was very similar to Gilbert's. Ooh, do you remember which book it was? Was it, is it Friedberg? Insel and Spence? That's the one that we used for my second course in linear. And then another one that I know exists is, I'm blanking on it right now. I feel like it starts with an A, but, geez, I'm blanking on it. There's another one that'll come to me in a second here. But I like this one. This one was nice. Not 100% sure if the first name was Friedberg. Something, what was it? What is that book? Yeah, okay, I got it. Friedberg, Insel, and Spence. That is correct. Oh, you're taking advanced linear this upcoming semester. Really? Dope. Okay, well then look at that. You took linear algebra in college. You might give it a shot again. It sounds like you will give it it sounds like you will give it another shot, right? Given that you're taking another class in it. All right, so I think that's it. I think we're done. 119. I'm gonna go ahead and cross it off. I think that we did it. I don't know if there was anything else we're supposed to do. Next one. Strang. Did we do, let's do 12. Why not? Let's just keep going. Let's do them all. Strang 1112. What's going on in this one? All right, so problems 12 to 15 are about these diagrams. Okay. Cats are acting up. Okay, it says four corners of this unit cube. Okay, we're gonna have to draw this. So we've got a cube. It's been created. It's just kind of hard to draw perfectly reproduce. I should just show the dang book on screen, right? They're not gonna care, right? Maybe they will, who knows? Let's play it safe. Okay, so this is sort of what the drawing looks like, and it has I equals 1, 1, 0. K is 0, 0, 1. This is J plus K. And J equals 0, 1, 0. And then there's a weird note that says, notice the illusion is 0, 0, 0 at the top or bottom. I mean, I think it's at the bottom. I think it's just... Oh my god, okay, now it's shifting on me. It's shifting on me. No, yeah, like this is... Yeah, it's at the bottom. Yeah. Yeah, it's just... It's this little note. There's like a little note right here, and it's confusing me. So I'm not even going to read it. Ignore that note. It doesn't need to be there at all. Okay. Four corners of this unit cube are 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. What are the other four corners? Other four corners. Find the coordinates of the center point of the cube. The center point of the 6 faces have coordinates blank. The cube has how many edges? Okay, so there are a lot of questions in this. So I see, here's question 1. What are the other four corners? Then it says find the coordinates of the center point of the cube. I mean, is this just a hint? The center points of the 6 faces have coordinates, blah, blah, blah. The cube has how many edges? I'm a little confused. All right, so 4 corners of the unit cube are 0, 0, 0, which I think is this one right here. 0, oh wait, oops. 0, 0, 0 is that red dot right there. 1, 0, 0. 1. Okay, this I equals 1, 1, 0 is confusing me. Is that correct? Is that really correct? I equals 1, 1, 0. I would have expected I equals 1, 0, 0 here. How... Okay. 1, 1, 0. So it's saying that it's going in the J in the second coordinate direction as well as... I don't understand this at all. This looks like a typo. But we're in like the 6th edition of this book, so I feel a little skeptical that there could be a major typo on the first problem set. Like, maybe that's just me. That seems a little strange. Am I reading this weirdly? So is that what the hint is about over here? This note that I don't understand? I don't get it. Let's put a big question mark on this one and move on. Oops. I need to take out all my talking out of this performance. That's so annoying. Let's keep going. Strang 1.1.13 says that this is a review question. In XYZ space, maybe I'm just bad at imagining 3D space like XYZ space. I feel like I've never been very good at that, but I can do it okay. Where's the plane? Like, I can't draw very well. Where's the plane of all linear combinations of I equals 1, 0, 0, and I plus j equals 1, 1, 0. Okay, I plus j equals 1, 1, 0. That makes way more sense. Yeah, because like it says that these questions are about this cube. That this cube, like all these questions are about it, and here it has I equals 1, 1, 0, but then down here it says I plus j equals 1, 1, 0. That makes more sense. Like, this should be I, this should be marked I, and then like I plus j, I really think should be like, wouldn't I plus j be this one? Or something? Yeah, like wouldn't that be that one? 1, 1, 0. That would make way more sense to me. Like, I'm pretty sure that this really is a typo. Apologies for the noise. It was my cat when we recorded this beautiful music. Okay, we gotta change that. How's it going, everybody? Anybody out there? Anybody else studying mathematics? Who is a math major here? Who studied math in the past? How's it? God. Okay, that's so annoying. Apologies. All right, so we have XYZ space, the plane of all linear combinations of I and J. So we're talking about all linear combinations of I and I plus J, where I plus J is this other one here. Well, that is going to be all of R2. I mean, it's hard to, I don't know how to draw something like that, but it is everything in I don't know if that makes any sense at all to anybody, but like it is the flat 2D plane R2 because any AB0 can be written for sure as a combination of I and I plus J, because we can get 0, 1, 0 as I minus I plus J, right? So that is a linear combination of those two vectors, and then therefore this is A times 1, 0, 0 plus B times 0, 1, 0. This is A times the vector I, and then this is B times I minus I plus J. And now we have this linear combination, A plus B times the vector I plus, or what I meant to say is minus B times the vector I plus J. So if we marked these as like V and W, this is A plus B times V minus BW or something. Could be any vector AB0 in R2. So I think that that is a slightly sloppy proof that all of R2 is spanned. Spans R2 because I and I plus J are linearly independent. You can't write the two there's no multiple of I that can equal I plus j. There's no way that you can multiply one of those two vectors to equal the other. That's impossible because you have this 0 term here. And there's nothing you can multiply by 0 to equal 1. That's impossible. So, yeah. I think that the answer is just R2. I'm gonna call it done. I think it's good enough. So we're going to put a question mark on 12 on our little status sheet and mark off 13. Cool. Problem A. What is the sum V of the 12 vectors? Interesting. This is an interesting question. So this is asking, it has this diagram of a clock, and it is a standard clock with 12 hours in it. So I like to draw my clocks this way. So I start with 4 of them, and then I split each of these with 2 more. So 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the question was, if we called each of these a vector, like v1, v2, v3, v4, v5, v6, well, yeah. Let's do it like this, yeah. V12. So now, I mean, I don't know if everybody sees it. I just want to make sure I write it out carefully. We're going to have this vector plus this vector in the opposite direction. They're going to cancel each other out because they're the same length. They're the same length, but pointing in opposite directions. So, how do we... I don't know how to write it exactly carefully, but like v1 plus v7 equals 0, v2 plus v8 equals 0, ... until we get v6 plus v12 equals 0. So every one of them, every vector coming from the middle of a clock has two hour signs on opposite sides of the clock from it. And if you take those two arrows and add them together, then they add to 0. So then the total sum is going to be 0. I don't think we're going to be more precise than that. The sum of all the vectors is 0. Nobody's grading this homework set. Number 14b. If the 2 o'clock vector is removed. Oh, interesting. Why do the remaining vectors add to 8 o'clock? Well, basically, it's exactly the same reasoning that I just had, that we had the sum of all these, like, what is the pattern exactly? Plus 6? Yeah, like a half hour away would be 6 hours away. Where I goes from 1 to 6. If V8, oh wait, no, if V2 is removed, then I don't know. The term V2 plus V8 in the sum is just V8. And then the rest of them still add to 0 without that pair. Yeah, that's not ultra careful, but I think that makes sense, right? To you all, does it make sense? I think it's a little. We gotta work on our mathematics here, y'all. Let's give this like a little yellow mark on. I'm not really thrilled. This is like a medium on my my explanations. String 1114. We got this one. It was a yellow. Oh, we should start doing like. Ooh. All right. Whoops. Let's stop listening to YouTube. How's it going, everybody? This is a little strange, right? Is anybody enjoying this? We're working on Strang. Strang problems. Part C of String 1114. Let's see. The components of that 2 o'clock vector are V equals cosine theta comma sine theta. What is theta? Okay, So now we are actually going to put on our thinking cap. And we're talking about the 2 o'clock vector here. So if we remember our trigonometry, we have the special right triangle, or we have the special values of a triangle at theta equals 30 degrees, theta equals 45 degrees, and theta equals 60 degrees, and theta equals 90 degrees. And so this question is asking us about when the hour hand is 2. So I know that it's this one. I know that it's 30 degrees because we split equally from 0, 1, 2, and 3. So then this angle here needs to equal this angle here, and they both need to equal that angle in the middle. So then 3 theta equals 90 degrees. Theta equals 30 degrees. Like, this is just confirming that, yes, it is this special angle, 30 degrees. And yeah. Components of that 2 o'clock vector are v equals cosine 30 sine 30. What is theta? And yeah, hearing cosine and sine made me really think about the unit circle from trigonometry. If we can review for a second, the unit circle has special values. Root 2 over 2, comma 1/2. Wait, is that right? I forgot. I have forgotten. Okay, so the unit circle is the unit circle with length 1 of radius. The radius is length 1. So these are easy. 0. This one is 0, 1. This one is 1, comma 0. Okay, so that's that one, and then there's one more in the middle that I am blanking on at the moment. I'm pretty sure 1/2 root 2 over 2. Is that right? And then this one, I feel like we should be able to figure this out geometrically. Because we want x squared plus y squared. X squared plus y squared equals 1. And because the angle is a 45 degree angle, I know x and y are equal to one another. 2x squared equals 1. X equals, yeah, this is what I was feeling was there's something wrong. 1 over square root of 2. This is, yeah, I thought so. Oh, wait. 1 over square root of 2 is the same as, this one is root 2 over 2. Is the standard way to write that. Okay, so I was wrong What is the x-coordinate? It's been so long since I've been doing trigonometry. What is the x-coordinate on the unit circle? Y'all, it has been a very long time. I have forgotten. I have forgotten these things. I can't believe it. Unit circle, I'm blinking. What is the special angle at? Oh, square root of 3 over 2. That's it. Yeah. I knew it was like still a square root of something over 2. And I was like, I kept thinking 3/2. I was like, but 3/2 doesn't make sense either. All right, so it is square root of 3 over 2. You know what? Math is hard sometimes, and that's how we learn. We learn by making mistakes and improving upon our mistakes. Cool. So these are the special values of the unit circle, and from those you can calculate all of the other ones. You think of these as mere symmetries of the first quadrant. So don't try to memorize everything, kids. You can just learn one of the coordinates and then calculate everything else based off of that, I think. That's how I like to see it. Components are those. What is theta? Theta is for sure 30 degrees, which is the same as pi over 6. Any questions? How's it going? Luna, my cat, my beautiful cat. Okay, so we did 14. There's some squiggly, squishy things about it. It was a little yellow. I've been marking things red. I wish I would go back and mark them green instead. Mark them with green like these were easy. These were all easy to do. But regardless, let's pull up Axler, shall we? I want to take a look at Axler, and let's get a little bit of a different treatment of some of the same material. And I just feel like switching color now. Axler, his book is called Linear Algebra Done Right. And you can find it online for free, which is so freaking cool, isn't it? So I will pull it up on chat or on screen at some point in the future. But today, I'm just going to copy over a problem. The first problem is very different. It's immediately more theoretical. Okay, so we want to show this thing that we call commutativity. Commutativity in the complex numbers. So complex numbers are written like that with a C, a blackboard C. So I don't know exactly what we're allowed to assume or not, but I'm going to call this a solution. It's not quite a proof, but I don't know. Maybe we say A is A1 plus B1I, and beta is A2 plus B2I. No, I don't like that. I don't love that. I hate that notation. A's and B's are confusing me. Confusing me as heck. Alphas and A's are similar. Betas and B's are similar. So beta is B1 plus B2 times I. Right? With AI and BI in the real numbers. Then alpha plus beta, I guess like we're supposed to go from like a very precise definition of addition in the complex numbers. Where do we have the definition of addition? Okay, yeah, great. So if you're doing a rigorous proof like this, you need to really understand exactly what definitions the book uses for certain things. Like, what truths are we allowed to assume? Axioms. Like, what things has the book already proven previously that you can rely on and use in your own proofs. It says that the definition, axioms, and definitions. There are some things that are axioms. There are some things that are definitions. There are some things that are theorems. There are corollaries and other mathematical results. This is a definition, the definition of a complex number. I like this. Let's go with this. Let's write it down precisely. 1.1. The box also has yellow as well. So definition of the complex numbers. C. This will be good to show people who haven't seen like formal mathematics, I think. Like a formal definition in mathematics. A complex number. A complex number is an ordered pair. It is an ordered pair, AB, where A, B are both real numbers, but we will write this as A plus BI. Okay, so it is saying that literally it is implemented. The implementation, like the true, real thing that a complex number is just an ordered pair. AB in R2. Okay? Like an ordered pair, like a complex number is a point in two-dimensional space. R2. But we have some special rules about addition and multiplication that makes it different than just the regular two-dimensional plane. The set of all complex numbers is denoted by C. In Axler's book, he uses a bold C, and then in a whiteboard or a blackboard, or a chalkboard, you draw a little line on spots to make it look bold. That's called blackboard bold font. C is defined as the set A plus BI such that, I'm going to use a bar notation, A and B are in the real numbers. Okay, so that is, the set of all ordered pairs, A, B. And now we have addition, and multiplication. On C are defined by A plus BI times, plus C. So he's using ABCD, isn't he? Oh, yeah. That's good. C plus DI equals, so we add elements coordinate-wise. The real parts add together and the imaginary parts add together. B plus DI. So this is literally just the same as addition in R2. This is the same as adding two vectors in Euclidean space. Like if you have a point and you add it to another point, you're going to get a third point. And you get it by adding their coordinates together. Because remember, this is, again, the coordinate A plus B, comma, B plus D. So that's kind of cool. I don't know if I've really thought about that. Like addition is actually exactly the same as R2. But then multiplication is where it differs. That is where the complex numbers differ, because you can't multiply 2 points in the plane directly. You can do like the dot product or the cross product, but those are not the same as like multiplying two numbers, 2 points in the plane. You can't multiply 1 1 times 1 negative 1. But in the complex numbers, we do have multiplication. Let me check chat and see if anybody's there. Anybody there? I didn't think so. What's going on, folks? What's going on? I hope somebody's enjoying this. Maybe in the future. This is a super niche thing. This is admittedly a very niche thing, and I understand that, right? Oh, you are. Okay, cool. Are you enjoying it? Nice to meet you, Shady Glenn. How's it going? I hope you're enjoying it. So, let's see. Multiplication. Where are we right now? How's it going? I lost my train of thought. Multiplication is defined as A plus BI times C plus DI And now we multiply this the way that we multiply polynomials in, you know, the way we multiply polynomials, I guess. We do, let's write it all out. AC plus ADI, right? Yeah. AC plus ADI, AC, ADI, BI, BDI, ADI plus BCI plus BDI squared. BDI squared. And we have taken this definition that I squared is -1. We are creating that special rule. So this then is the same thing as AC minus BD, because we're going to treat that I squared as a -1. And I'm just going to go ahead and move that forward to the real part, AC minus BD. And then the complex part is going to be AD plus BCI. AD plus BCI. Cool. And then this is Axler's book skipped this. Axler skips that intermediate step and just says, this is the definition. Which I don't think is great, because then you're like, how did we define that? Why did we choose that? And it is because we want this kind of property. We want this property where the I squared term is, turning into a -1, I guess. So here's the definition of multiplication and the definition of addition. And we can use these in our proof. So in our proof that we're working on, we know I used A1, A2, B1, B2. Axler used A, B, C, D. But whatever you want to use, you can use. That's okay. Alpha plus beta is A1 plus B1. Addition is super easy, y'all. A2 plus B2I. So we added the 2 points coordinate-wise, like from each coordinate. Now, we are going to use the commutativity of addition in the real numbers, which I think that we're allowed to assume at this point. Commutativity of plus in R. Some books will write that to say this binary operation plus in this math world R. So I think that's okay. By the commutativity of R, of addition in R, this is the regular old addition that we all know and love in the real numbers. A plus B equals B plus A. So I can swap each of these terms around the plus signs on the inside. Like, we are not doing a circular definition here because we are assuming commutativity of the real numbers. We are not assuming commutativity, we're not assuming it of the complex numbers. Like there's a difference, I suppose. Now, this is, by definition of, by the definition of addition in the complex numbers, now we have that. QED. Yeah, I mean, I think that that's decent. I think that that's a decent proof, little proof. But notice, for anybody who's seeing this for the first time, notice that there's very few numbers. There's not really any concrete examples, or this is not like solving one single example problem like in Strang. All of the exercises had like specific vectors that we're working with, or like concrete, like really concrete examples, calculating a number, calculating an angle, and other things. In this one, it was a little bit more abstract. Like we are proving something no matter what numbers, no matter what complex numbers we have, we can always add a plus b, or alpha plus beta equals beta plus alpha. That's kind of cool. I think that's really cool. Like, this is an example of kind of proof-based mathematics that I hadn't seen when I was younger, or in high school or anything like that. And so I think it's kind of cool to try to mix the two together. Just smash it all together in this YouTube Shorts stream. You all just ran into this because you're on YouTube Shorts instead of doing your homework. And now you've randomly got assigned this math lecture, which is funny to me. Unless some of you all are subscribers, like and subscribe. Nobody hit the like button this whole time. Y'all don't like this stream? Come on. All right. I suppose it is what it is. Let's move on. Let's do another one. If we have time. We don't have time. I gotta go. I gotta go very soon here, y'all. But we at least got one of those Axler problems, and I feel pretty good about it. I feel happy about it. I'm giving it a green mark. I want to practice all of these again, these Shilov problems. They're all kind of a little tough. All of these Strang problems have been easy. I do not need to review these. Except for this one. Number 9, I don't know why. Oh wait, no, what was 9? Why did I mark 9 like that? That was just saying I wanted to work this one today, and we did do it. Number 12 I had a question about. It seemed very confusing. Number 14, I do want to come back and try again in the future. So let's give that one, let's self-rate ourselves with a little yellow on that one. But we have worked it. I wouldn't call it hard, but we're making progress, y'all. Hey, thanks for the likes. I appreciate it. Like, honestly, no joke, it helps so much, especially as a new channel. This is my second channel now, and I'm trying to fix the mistakes that I made in my first channel. And I know that shamelessly asking for likes and subscribes is actually pretty important. So thank you all. I appreciate it. I'm feeling good. we made some progress. We solved some Strang and we solved some Axler. Just for y'all, if anybody who wants to do some homework and think about a math problem as you go to bed, as you fall asleep tonight, or as you go about your day, as you're waking up, whatever time of day it is, if you want another math problem from Axler, the next one is 1A.2. Show that alpha plus beta plus gamma equals alpha plus beta plus gamma for all alpha, beta, gamma. Why am I writing lambda? It is lambda. Why is he using lambda? Like, yeah, that's been bothering me. I'm like, the next letter is gamma, but why is he using lambda? I don't know. I think he just thinks that lambda is a fancier looking letter. Like, the next one should be gamma. That is why it looked so weird to me when I read it the first time. I was like, that's not normally what it is, right? It's been a while. I have not done math in a while. For all alpha, beta, lambda in C. So basically we are proving associativity of addition in the complex numbers. So give it a shot, y'all. I think that you can do it. I believe in you. Try to rewind and follow a little bit the steps that I took to prove this one. Like, try to set up an equation. And I like personally my notation of A1, B1, because then you have like A1 is the real part of alpha, B1 is the real part of beta, and then I guess C1 is the real part of lambda. I don't know. I would like that. Like C1 plus C2I. Let me write that so you see what I'm saying. Like, next we're going to have lambda is C1 plus C2I. And then, as a hint for the problem, we're going to write what alpha plus beta plus lambda equals ... equals ... Well, it's kind of redundant to have two ... but you want to start from the left-hand side like that, and then you want to end with the right-hand side like this. And if you can do the steps in between, if you can do that derivation, then that is the proof that the two are equal. The whole challenge is in this ... right here. So give it a shot. I hope that that you're able to give it a try. Thank you all for watching. Oh no, the iPad stream is frozen. Is it really? How long has it been frozen? Oh my god, has it been frozen for a while? Woof. Why? No. Why? That's so confusing. Streaming is hard, everybody. You don't even know. You don't even know how hard streaming is. This is so weird. It's working for the other thing, but not this one. All right, so I'm going to do this. I'm going to do this. Now it's working again for whatever reason. That's so strange. Well, I apologize. Thank you for calling that out. But yeah, so the goal is alpha plus beta plus lambda equals dot 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 parentheses alpha plus beta plus lambda. That's your goal. Yeah, so it looks like the iPad got stuck while writing out this proof for Axler 1.1. That was a while ago, so oh well. Here, just want to make sure everybody does have this. If you want a practice problem, the next problem is show that alpha plus beta plus lambda, blah, blah, blah. We're going to show associativity of addition in the complex numbers. So, happy mathing, happy math practicing, everybody. It's nice to meet you all. I am the math hobbyist. And I hope you have a great day. Thank you for watching, everybody. Like and subscribe. About 5 minutes for me. It could be me. No, it was totally stuck. I don't know why. That's really annoying. I'll try to keep up OBS so I can monitor whenever those sorts of bugs happen a little bit faster next time. It's back again. Thanks for the stream. Yeah, thank you. All right. Have a nice day or night or whatever time it is for you. All right. Bye. Thanks for watching.